I think since I cannot speak really, like sometimes it's really a little bit hard, but it's okay. I can still speak. Well, let me continue. So last time, I think we did all of this in the Saturday class. So I will review what we have. It's just a quick review. So basically, this is about the fundamental theorem of calculus, which we are going to combine all the derivative stuff and the integration that we are going to see in the future. There are many techniques for the integrations that they already have in one separated chapter in your textbook. So all the techniques of integrations, okay? And we are going to see later. But for now, let me just take a review and just go to the conclusion from the fundamental theorem of calculus. There are two parts. Okay, there are two parts of the fundamental theorem of calculus. Part 1 and part 2. Part 1, we can set up a function. It can be g, it can be any function you can write here. You can write this function as an integration from a constant to a variable, which means this is, we can say it's another function because it's not defined in the constant. Because it is from a to x. Okay, often another function, we say we have f, and we introduce another variable t. Okay. It can be any variable, but usually the textbook write as a t. Okay. So why we need to have these different variables? Because we are going to use the t to basically state the meaning of inside the integrations, okay? And then the other variable will be the result if we integrate this. Okay? So if we have a certain function, and then, for example, if we have this g, and we would like to derive, find the first derivative of this g, which means find the g prime. So what you are going to do based on this, and based on what I think some of the proof that we have seen, is basically the first derivative of g is basically removing this integration and substituting x to t. Okay, so we are going to have this expression g prime x equals f of x. Okay, so this is the first part, and of course all the statements need to be first it need to be continuous, differentiable, so that we can differentiate, and then to differentiate is basically you need to have a continuous function and differentiable function. Okay, so of course this should be half, and then we have this. So since we are still using our derivative, I hope you still remember when you observe the graph, like the concavity and all the things. So you need to still using that, but the function, maybe the function will be having this integral. Okay. And another part is where we have this. Okay. Suppose that f, the capital F, we call that as antiderivative. Okay. Antiderivative of the small f. When we derive this capital F, it is equal to the f. Which means that when we are having our integrations, we call this integration definite integration, which we have a constant and another constant, which we can compute. And then if you are using your calculator, you can compute using calculator. You can set up the numbers, and basically you are going to compute the integration. So basically, this means that the differences between the b and a is we can plug into this antiderivative system. So fb is f of a. We call this the net change theorem, another terms. So if you are reading the books and you find the net change theorem, that's the same thing. This is the net change theorem.
Okay, and basically the whole thing within this section is basically just two things. So if g is in the function of this integration, so the integral is a function itself, then we can have this g prime is equal to f. Okay, that's the first one of that. And the second one, if we have the definite integral of f, it means that we can basically take the antiderivative form, or we can say we can integrate them and then plug in b and a, and then it's going to be f b minus f of a. Okay. I think some of you are already familiar with this, but this is just to make sure and confirm that we are on the same page. Okay. So that is the fundamental theorem of calculus. But visually, or if we are going to look at some, at least like a simple application of on how we are going to understand what this is about, we can simply take some time to draw a graph. So let me go back here and then. So if f is a function that is on this figure, so y is equal f of t. Now we are on the variable t. Okay. And then we define g is that integration. Let me write in a clear way. Okay. If this is our function, so now we can treat this integration as a function. Okay? So whenever you see integration and then we see some constant, and then the other endpoint is another variable, it's a function. Okay? It's a function. It can be also a variable and just some number, or variable and variable. It's also a function. We can see later how we are going to deal with that. But now the question is, if we want to find the values like g of 0, 1, 2, 3, 4, and 5, and it is going to like sketch a rough graph of g. So basically, what we are going to do is we are going to input our x. Okay, we are going to input our x. So if we input our x equals 0, it means that it's from 0 to 0, which means nothing, right? It's 0. So let me just write here. So basically this is going to be 0, right? And then g of 1, basically it's 0, 1, ft dt. But what does it mean? We don't even know what is f, but we know the graph. Integration means that the area under the curve, or you can see under or above the curve, okay? According to this axis. So when x equal 1, what will happen here? So when x equal 1, so you see here, this is the area of the triangle here. So this is g of 1. So we can have the triangle. Let me write half, and then 1, 2. Or this is just 1. We don't know whether it's meter or anything, but we know this 1 unit. And we can do the same thing with g of 2. Now g of 2 means that it will be starting from 0 to 2. So 0, 2, so it means that it's going to be this area. So the triangle plus the rectangle. So you might be maybe wondering, like we have t, okay,
and then this is x. Where is x in our graph? So again, this t or any variable inside is actually just a symbol that is going to. So actually, let me say this: with x and t is actually they have the same the same construction. The difference is, if you see anything like this one and this one, it means that at the end of the process, you are going to plug in the x in here. So which means that at the end of the process, we are going to plug in 1 to this f1, right? Or if we say the antiderivative will be f1 minus f0. Okay, I hope you get that point. Okay. So the same thing with the g of 2. We are going to plug in like this, and in the picture we get another area here. So 0 to 2 will be the triangle. This will be this plus 1 to ft dt. The first one is the triangle. It's just 1, so plus. The second one is the rectangle. 1 multiplied by 2, or this is just 3 if we plus. And do the same thing for the another one here, but this is, we cannot really compute how with this, so we need to approximate the value. But if you are willing to observe that the actuality for our integral, even though this is the using the fundamental theorem of calculus, so the integral is actually the whole area here, and then the rest is up to here. This is 4, 5. You can see that we can have here, and then maybe the last one is here. And for all the region above this axis, above this p, this will be the positive. Okay? If you have the below, it will be negative, as I think we mentioned last time also. So this will be the negative region. This will be the positive region. Okay. Okay, now I would like to move to just some example. Okay. Okay, no need to find it 3, 4, 5. You can, but you can approximate like how it is. Okay. So let's see the example. Maybe I will use this part here. So example is find. Let me just use the textbook.
About the previous one.
Yeah.
So when you calculate the one in between 2 and like until 5, like so 3, 4, 5.
Yeah, I didn't do it because we need to approximate.
If we do need to do it, we need to use.
I will not give that question.
Oh, so we don't need to learn it for now.
No, not learn it, but I don't give more information.
Oh, so
You need more information if you want to compute. Okay. Yeah. Okay, so I think let me rephrase this. Okay, the question is asking like G3, 4, and 5. But actually, you need to know like what is this f, okay, to compute all that number. What you can do is basically, if you don't know anything and you want to compute, you can approximate. And how to approximate? You can check with some
quadratic functions, or I think some quadratic functions or any polynomial functions that can be approximated using the x equal 3, that is going to be exactly here at 0, so this will be 3, 0. So you need to have the roots of there, and then you have to have the roots here, and maybe you can approximate this, and then this will be the same as half of this, right? Or this is half of this one. But I don't, because this is not a full complete question that I won't give in the exam. So yeah. Of course, this is just to show you that the integration is actually the area, okay, of another curve. Well, if you read the textbook just gives you the approximation that this is going to be. Let me just write your approximations in the textbook. Okay, so g of 3 in the textbook is 4.3. It's 3. 1.7. So again, this g of 3 means the whole thing up until x or t equals 3, and then g of 4 is all the things, the first one minus this, okay. And then this last one, all the things minus this, okay. Okay, back to here. I will write some example. This is secant t dt. Or maybe let me write two questions. Okay, the first one is maybe this one. So if okay, so we have two questions. So maybe the first one, okay, the first one first, okay. The number 1, we have integration from 0 to x of the square root of 1 plus t squared dt. Okay. As I mentioned, we have g, we want to find g. So basically, because g is having the integration, and at the end of integration, you are expecting to put in all your numbers inside, or put all the endpoints. Right? Since one of the endpoints is a constant, any constant, we have proved, right, last Saturday, any constant you put, at the end of the process, it will be gone, it will be cancelled. The only one you have is when you put x. So put x here, then we can pretty sure that this is basically just substituting x with the t squared, right? So basically this is just writing as 1 plus x squared, and then done. Okay, and then done. Okay. Now let me change a little bit. Before we go into this one, let me change a little bit. If let's say now g is changed to 2x. What will be the g prime? Now it's 2x. So the idea is to substitute
to this equation, right? But how about if we change the x into 2x? Or maybe any other variation, maybe x squared, maybe x cubed, maybe square root of x, maybe ln x. It can be, or it can be like the whole equation like polynomial x squared plus 3x plus 1 here. What can we do? Any idea? Or you could think this as a, this is constant, and maybe this is just a h of x, okay, and this will be f of t dt. This is g of x. So basically, remember that whenever you derive a function, if the function has a complicated one, maybe inside those functions there will be another function, right? So we are going to use the chain rule. Okay? So we are going to use the chain rule. So for this one, we are going to have f h of x, and then multiply with h prime x. Okay, that's the basic principles. So it's actually similar principle from what you have done before, the derivative, the chain rule, and everything. So now we are going to implement all the derivative stuff that we learned, but then we are going to introduce how to get into this integration, and then how to combine this integration with the previous derivative. So basically what we have here, substitute here, and then multiply with chain rule. Multiply with 2. Okay. So this will be equal to 2 . Okay. Maybe too much process that I skip. I will write down later how we get here. Sometimes we could get the better understanding of chain rule if we substitute with some other variable. Substitute these two x's. So we can still write, for example, let using u as 2x. Okay, so if we are taking this u as 2x, and if we derive this u, so du become 2x dx. Okay, or here we can get du dx is it's not 2x, it's supposed to be 2. It's 2. Okay, now we can write the whole integrations 0 to u, okay, and then still this is the same, and when we derive this, we can treat as only single variable, right? But actually when we write here, when we take, let me write here, this is d du, okay, and then this will be 0 1 plus t squared dt. Since g prime x, right, it's not u, so we need to multiply something that will have the end result as x. Okay, so we need to take this into chain rule, multiply with du dx. All right, okay, this is actually, let me write with this. Okay, to make this equal to the right side, then we need to multiply with du dx. So that we are going to have this. Right? We want to differentiate with respect to x, but since we are letting the function become u, we need to have the definition altogether. So u is 2x. So du dx is equal to 2. Which means that du dx here will be this. And basically this part is just substituting here. Okay.
So dg dx will be, this is 1 plus u squared, du dx is 2. And u squared is basically 2x squared, or you can write 1, or maybe let me write 2 in the front plus 4x squared. Or this is the g prime. Okay.
Perhaps it's like too many hassles, right? It's like really long steps. But actually, you can think like substitute to the functions, multiply with its chain rule. That's the best way to do. Or you can state with it.
You can state from with the right one there. Okay.
So basically, u prime x is the functions you put inside the f, and then multiply the chain rule from the endpoints, the h prime. Okay. I'm trying to explain like what's happened in the middle using the substitution with AU, okay, to help you to get the idea why this happened, and why we can just sub and then multiply with chain rule. Basically, we are substituting something here, okay, and then because we changed from the x to u, then we need to multiply with something that need to be getting x at the end, because we want to have dx, right? Okay.
Okay, any questions?
Okay, if you're confused from now, like this one, this is a very simple one. So it's better to ask now before too late, before it's getting the final exam. If you ask many questions nearby the final exam, bye bye. See you next year. So if you are like curious, like now, like I'm still confused about this, just let me know. Okay, maybe we can still discuss on the class, or if not, then maybe we can discuss after class. Okay. But actually, at the end of the day, okay, no matter how understand you are about this, you will always find a pattern or identification how to solve this based on the pattern, or how to make out the solutions, okay, from what we have done here. Okay. You don't really need to know like what's happened with this and that, as long as you know that every time you sub into this one, sub the endpoint here, and then multiply with the chain rule of this, you will always get the answer. Okay. The problem is sometimes it's not always like a normal like this integration. Let me give you
Another point of view, or another example. Okay. Okay, another example. Maybe check first this one. Okay, let's say we have h of x. let's say this is A and this is B. Okay, I'll try this one first and see if you can figure this out. If you can handle this much, should be okay, should be fine. Should be fine. So we are not completely yet fully go to the integral section, which is having many techniques. We are still in the middle way to learn what we have in derivative and apply in what we call the fundamental theorem of calculus. Which one? The previous one? The previous one here. This one? Okay. And you can repeat the process all the time using the fundamental theorem of calculus. So if you find the first derivative, sub the variable x into t, multiply with the chain rule, and it will work all the time. The problem is if you have something a little bit different in the integration, so that we need to perhaps rearrange the structure quite a bit. Yeah. Okay. I think the first one is quite simple. So you could get directly the h prime x as we substitute inside, right? And then multiply with the chain rule. So this will be x over x squared plus 1 and then 1 over. And I think I'll just stop here, just make sure. Okay. For number B, all the examples we had before, it's always a constant to x, a constant to some functions, right? Now we flip a functions to a constant. Now how we are going to deal with this? Now we can treat this as similar what we have done before, but we can flip the endpoints and taking negative. Okay, so we can do that as a property in integration. I think I've done that last discussion. So this will be, let me write first. This will be equal to y and then negative pi over 4 square root of x. And now we can solve. Okay. So we can find the y prime by taking all the function inside. So we have negative and then multiply with 1 over 2 square root of x, or we can say this will be negative 1 over 2 tangent square root of x.
That's right. Minus half. Minus half. From where minus half? Oh no.
I think I have given you some of the proof. Okay. Let me. Do we have? I think. Wait. Let me check for a while. Okay, whether I have given you. Okay, I think this one should be. Okay, here. So no matter how the constant will be, in the process it will be cancelled. In the process will be cancelled. So it will be 0. Any constant will not matter. It will not matter. Okay. So then this one here will be cancelled. Will not matter.
When does the derivative integral ends with us?
When it is indefinite integral. Indefinite. We are not yet there. This is still derivative actually. Still derivative, but we derive the integral. So okay. So like for example, we have pi over 4. It's meaningless here because it will getting cancelled at the end. Now another case is the endpoints are from a function to a function. Okay? We can also have that case. Okay. So for example, let me just write first the equation. So C. Let's say g of x is so asking the g prime. Yeah. Oh, the negative sign coming from the flip endpoint. I'm flipping out the endpoint. Yes, I'm flipping the endpoint and go minus. Yeah.
After you flip the endpoint to the negative sign, I don't apply the negative sign to both of the parameters. Don't have the negative sign to the first one. Yeah. Don't apply to both of them.
But this is already one, right? Already one.
I don't apply so that it's negative square root of x.
Okay, I understand. I think it's really elementary. Okay, so let me show you what you need to do. Okay, so my suggestions: every time you did some process, place a bracket. Let me show you. Minus, I will put a bracket here. And you will see that it's actually the same. So negative, bracket, and then we can substitute here, right? And then multiply with this. The same? Okay, so bracket is important. It is sometimes really helpful when you have a complicated process, and you can like extend like which one is the group that you want to do. So bracket is important. Okay, now number C. Now we have a integration with the endpoints both are functions. How we can deal with it? Any idea? Yes? Yes. Yes. Correct. Correct. So we are going to separate this, become a two different integrations. Okay. So first is we need to think what is a constant between these two. So we can think like in between this 1 minus 2x, we need to have some constant that should be true for all conditions. And I think if you think like C is 0, I think 0 can be proven to be in between these two. At least it can be done, right? So let me erase this first. So we can check then when c is 0, we can rewrite the g 1 minus 2x up until 0. And then from 0 to 1 plus 2x. Okay? And then the rest will be the same. So we can flip this. And basically we substitute everything inside. Okay, let me substitute back. So this will be 1 minus 2x sine 1 minus 2x, and then we need to multiply with minus 2. Okay, let me just finish off this. Okay, so negative will be 2, 1 minus 2x sine okay, and then done. So this is the g prime. Okay, I think we can have a break. Okay, let's continue. I think I forgot to give the process of this one. So let's find this. So this one will be equal to secant x to the power of 4, and then multiply with 4x cubed. Just that, or you can rewrite. Now, another typical question for the fundamental theorem of calculus is to analyze the curve. Okay, so if we have, for example, let me give you this expression. Okay, the question is on what interval is f of x increasing, and all the questions that is supposed to be in the derivative, especially the curve sketching, increasing, decreasing, and then concavity, it can also being asked within this sections. Okay, so please don't forget the whole curve sketching. I know, like, maybe you didn't going well on your but don't forget that. Okay, I know that. Okay, I hate this, and then you forget that. If you forget like the half part of the semester, you will not be able to go forward. So I haven't yet checked the makeup exam, but from what PA says, maybe not good. So I think when I see, I will readjust the score, and maybe because there's one question that is actually I'm not planning to, but I make it anyway. So I think I will readjust the score for the makeup. Okay, so this one, okay. The question is, what interval is the function increasing? Function is this. So we need to accept that now this integral is our function. Okay. So the idea is still similar, very similar. That is when we say the function is increasing, it means that the first derivative, right? The first derivative needs to be positive. Okay, so we can just write that first. So increasing is when the f prime is greater than 0 or positive. So then we can take the f prime x from the function, and because this is just from 0 to x, we can input the x inside the integrations, which is going to be 1 minus x squared, and then e with power of x squared. Okay. And then maybe we are going to find the critical points if it has a critical point, so we can let this equal to 0. And because e, the exponent, is a positive function, right? It's always positive. Okay, so we can write this as positive function or function. So we can focus on that x is going to be either plus or minus 1. And then, as I always mention, just draw the line number, taking negative 1 and 1, and then check whether it's positive or negative. Okay. So check negative 2 will be 1 minus 4 will be minus, right? And then in between we can check 0, which is positive. We can check 2, it's also negative. So it's going to be down, okay, or decrease, increase, decrease. So we know that on so f of x increase on another notes that I think also you need to be aware of. Okay. So if we, for example, if we have like integrations from 3 to 6, and then this is just 1 over x dx. Okay. So the integral of 1 over x is plus x, absolute value. Right? So let me write here, or maybe let me write. So if f of x is 1 over x, then the antiderivative is ln with absolute value x. But since we have 3 to 6, it's all in the positive value, right? So it's okay if you write just ln x. It's okay because we have in the positive axis, right? Okay. So we can write this as ln x from 3 to 6, or ln, we put it 6 minus ln 3, or ln 6 over 2, and then become ln 2. Okay. Okay, now the other part that is quite interesting is, let me give you another one. Okay, 1 over x squared. Okay. Okay, and integrations, I think I give you, so if we have the xn and you want to integrate, this is basically xn plus 1, and this will be 1 over n plus 1. So what would be the result? So we can write the x minus 2, right? And then plus 1 become minus 1. So x minus 1 over minus 2 plus 1 to minus, right? So minus x minus 1. If you are maybe, every time you do the integration, if it is the simple one, you can always check, revert back, derive again. If it's going back to the original one, then you are correct. Okay. So let's see this one here. So x minus 2 dx. If we integrate this, well, we could check that, oh, perhaps this is the answer. Okay, maybe plus c. Perhaps this is the answer. But let's check. We can check through the derivative. So minus, go here, positive, minus 1, becomes the same. Right? So this is correct. So we can write that as our approach. So minus, and put back the number. So negative 1 over 3, right? Minus minus 1, right? So negative 1 put inside is 1, but it's minus 1, right? Okay. So it seems that is this our answer, right? But I will put question marks. Okay, if you remember, or if you want to try to sketch the 1 over x squared. So 1 over x squared, what will be the graph? It's going to be this, right? At least this is the graph supposed to be. If you check the GeoGebra, you can draw 1 over x squared. I think this one should be right. Without any other curve. Different with 1 over x. 1 over x, we have the negative part. So because you can imagine, like, because it has squared, all the negative become positive. So this is a positive function. But our answer is negative. How? Do you see with the logic? This is a positive function where you couldn't have any negative. But our answer is negative. Right? You get the logic? That means that there's something wrong with this. So you can see that this is negative 1. Where's negative 1 here? And then, does it continuous from here to here? No. So because it's not continuous, then this is going to be wrong conclusion. So we can write here that the f of x equal 1 over x squared is not continuous on, or we can also write that f has discontinuity, right? Discontinuity at x equals 0. But later, at the end of our, our section, almost the last part, we can try to compute this. We can. Actually, we can. But for now, it's impossible. It's impossible. Later, we are dealing with something like this, but later we can. So we can. Okay. So as for now, this we can write does not exist. Okay, now the next sections we are going to move to the indefinite integrals and some techniques. Okay, so let's see some of the table here. But before the table, let me give you a brief. So suppose that the f is antiderivative of the small f, and we call this indefinite integral. Which we can write the f of x dx become this antiderivative, or okay, the complete one for some specific functions and some property. I will let you see some part of it. That is, I'm not suggesting to memorize this, but I think you can keep some of them. Okay, some of them, not all. Like the last one, I think we are not going to use it. The hyperbolic trigonometric, the hyperbolic function, we are not going to use it. So the other one we are going to use the inverse, and then the trigonometric exponent, the normal exponent, the e, all we are going to use. Constant. Okay. So another thing in indefinite integral, that is going to be what is the difference between the definite and indefinite, is this constant. Okay. When you compute with the endpoints as a constant number, you are computing the whole thing. But sometimes when we are dealing with this, we are not sure what kind of functions that is coming before we derive or before we integrate. We are not sure. So we need to add some constant, because a constant, when we derive, becoming 0. Right? So, but we are not sure whether it has a constant or not. So we need just to add c. Because when we derive, the constant will be 0. Right? So it's also a possibility that maybe it has a constant. Okay. I think if you just see this form table and then try to place in your brain or in your storage, in your disk, in your drive, maybe you have too much information that okay, it's too full. Okay. So I think we can try some practice, okay, and how we can see how to write the solutions. So let's say we start from derivative. Okay, let's start from derivative. So if I have f of x and this is tangent x with power of 4, okay, if I'm asked what will be the derivative of this?
What is the derivative? Yeah, secant this, and then? For its cube, right? Okay. Very easy, right? Very easy.
So we can write like the secant squared x with power of 4, and then multiply with 4x cubed. Okay. Now actually, we can try this formula, or we can substitute, right? As we in the fundamental theorem of calculus, we kind of set up the substitution. So let's say we let the u equal x to the 4, okay, and then the u dx is 4x cubed. Okay, so this f prime x is actually, if this is going to be the tangent u, this will be secant squared u multiplied with du dx. Okay, as I think we mentioned before. So then we get the secant squared x to the power of 4 and then 4x cubed. Now I will reverse this. Okay, I will reverse this. So I will start with the 4x cubed and then secant squared x to the 4 dx. Okay. Now you kind of already have the answer and then the process in between, but we are going to tailor this from the integration part, which means we are going to find some variable or some component from this that need to be canceling out. Okay, so of course from our expression here, then we suggest that u is x to the power of 4. So let's start taking u as x to the power of 4. Because we know that if we derive that, it will end up with 4x cubed. So let this u is x power of 4. And then the derivative of this will be 4x cubed. Okay. And we can exchange this and make it into dx. So we can write that dx is 1 over 4x cubed du. Now, you see that this dx is here. So if you can imagine, if we put this into here, this 1 over 4x cubed will cancel this. Okay? So that's actually the basic principle. So we substitute, so this will be sub to here. Okay. So we kind of looking at 4x cubed secant x to the power 4, and then this will be 1 over 4x cubed and then du. And this x power of 4 we can substitute to u. Okay. Because we left u as x to the power of 4. And then we can cancel this. We can cancel this. And then we can have the secant. Oh, secant squared, forget the squared. And the integration of the secant squared is the tangent. Because if we derive tangent, we get the secant squared. Okay? So at the end, we have tangent u. But u is x to the power of 4. So we can write this is x power of 4. But now we need to add plus c. And this method we call the method of u-substitution. So how the method works is basically from this whole integration, you have to find which component that you can substitute with some u. Then when you derive that and then substitute the dx, you will find that it will cancel some other part of it and makes the equation simplified. So imagine that we take the x power of 4 because when we derive it has the 4x cubed. And then we substitute 1 over 4x cubed and we can cancel it. Okay. And then we have secant squared u, which is simplified. And then we know that the secant squared of u is tangent u. We can integrate that easily. Okay, so that's the idea. The rest of it, we need to have some familiarity with practice. Okay. But the idea is we find some components, we derive, and make sure that it will cancel the other part of the component. Sometimes if it's not fully canceling, you will getting some loops and then maybe not really solving the integration. Okay. So we can look on some of the example. And let me show you, at least there are several methods that we can apply, okay, from these u-substitutions. Okay. The last one.
I mean the precision.
This one? Okay. Okay. So let me give you another example in practicality, in which actually, like, there are like in math or in calculus generally, like if you are derive or integrate something, there are no limits in which method you are trying to apply. It can be like actually limitless. Like you can try possible other way if you can, and guess whether it's getting to the final solution or not. So let me give you some one example. Okay, so let me just go through just a simple one. Okay. So compute this indefinite integral.
This I will show you, like, at least we can have three possible methods. It's not too complicated. It's like simple x over square root of 1 plus x squared. Remember the idea is you can let all the components inside the function become like one single variable u. Or maybe you can use other variable like a, b, okay. Because sometimes in substitution, you try substitution one time, and maybe you have another like integration that you need to substitute again. So maybe you are going to use u, v, or maybe other variable. You can do this in many times, looping this substitution. Take the integration. Take the integration. Integral of x over that. Why loop it? No, this is integration. This is integration. No connection with the whatsoever. Yeah, that's like it. So because substitutions, like for one equation, you can have like many ways to substitute. Like you can try like as many ways. Like the more you try, the more you take failure. Now it's better than failure in exam, right? So just try anything. Try out. If you don't try, you will not know like how to do this. Okay, a bit easy, right? That's just it. I mean, using this one, it's you. You need to substitute. Yes, you need to substitute from here. What will be the component that is present? Yeah, you need to choose. So how to choose is when you choose, and when you derive, you need to make sure that it cancels the other one. So the integration will be in u, all u. The x will move on.
I wanted some explanation. I was hearing my.
So okay, let me go back to the previous one that what we did in this one here. Okay,
So basically, okay, why I'm using u equal x to the power of 4? Why I'm trying to substitute this x power of 4 with u? Because when I'm trying to do this, when we check the derivative and we substitute the dx here, we cancel the 4x cubed. So the equation becomes u. the x is over, right? So when x is over, we can integrate with respect to u. Okay? That's the idea. So when we look back on the question here, what kind of u that we can substitute from this function? That when we derive that u, we are going to remove all x. Okay, get out x. Okay, so see here, we have x. Okay, we have x squared, or we can see because it's a constant, it's 1 plus x squared, right? Now it should be obvious, and you should be later on. You are going to familiar when we have this x and we have 1 plus x squared. When we derive 1 plus x squared, it will become 2x. And you need to think in the future. Oh, 2x will be cancelled with x, right? So let's try to use that u. So u is 1 plus x squared. So du dx is 2x. So dx is 1 over 2x du. So when we place this 1 over 2x is going to be here, x will be gone. So this will be 1 over square root of u, in which we can integrate easily. Okay? You get it? The idea? So this will be, so x, let me write, this will be the square root of u, and dx will be 1 over 2x du. So canceling here, and we have 1 over 2. 1 over 2 can be factor out integral. So we have 1 over square root of u. Maybe if it is still confused, this will be and basically we are going to plus 1, right? Plus 1 the negative 1 over 2. And because plus 1 is just half, then it will be canceling the 1 over 2, right? So it will be u with power of half, and this will be 1 plus x squared plus c, yay. Okay? Or if you confuse this, this will be so this will be negative half plus 1 half, which it will be 2, 2 by 2 is cancelled. Okay, this is the first way. I will show you at least three ways. The second way, okay, the second way is we are going to use the whole square root as our substitution. So this will be u is going to be this. How is that possible? How is that possible? Wouldn't it make the derivative will be crazy, right? It's not crazy if we take squared, right? If we take squared, so u squared and then 1 plus x squared. Okay, we can do this, right? Derive this, and we have 2u du, 2x dx. Okay, and then we have dx is u over x du. And what will happen? Now our x over now become u. Now dx will be ux du. And this will be integration of du, which is u plus c, or u is the whole thing here, and then plus c. Okay, crazy, right? This one crazy.
Interesting. You can do this. You can take square, remove the square root, and do this. Basically, do the same thing. Take the x, substitute to the dx here, and then since we are u is the whole thing here. The first method is the normal method that we usually use, but you can also try take the square, maybe more simplified. Okay. Okay, that number 3. Okay. The whole thing? Yeah, sure. The third method, I think I mentioned several times, it's called the advanced guessing method. It's actually guessing, but for some reason, we can make it like more special. Okay, so let me show you. So we have here x and the square root of 1 plus x squared dx. Okay. So what is integral actually? Integral is finding a function like previous before we derive, right? But if we are talking in the derivative, so we derive. So when we are going back to the original one, we call that integrations, right? So let's say if we have the f prime as the x over square 1 plus x squared, what will be the f? And that's the question. Now you need to think what kind of function, when you derive that function, it becomes this. But then maybe your brain asking, but this is so complicated, it's x, it has square root. Remember, if you, like for example, take the square root of x. What happens when you derive that? 1 over 2 square root of x. At least we get some idea. We get this one, right? We get the square root. How about if we have, so like we basically try and error, but in a smart way, okay? So let's say we have, so if we take square root of x, the f prime will be this, right? And if we have x squared plus 1, similar to what we have here, we are guessing that the f prime will be 1 over 2 square root x squared plus 1, but multiply with the chain rule, x squared become 2x, so we'll multiply with 2x. So we get that, oh, we directly get. So within this statement, we can use this method, like when the f is some function and we derive, then we can conclude that the integral of this, okay? So the integral of this then will be square root of x squared plus 1 plus c. This guessing method is effective, especially for repeated functions. Like when you derive, you will see that it is always there, like exponent. Like e to the x is always e to the x, or e to the x will combine with some other functions. It will still have the e to the x. That you can think like, I can guess this before. Okay. And some, I think if we have time, we can try some interesting question, but maybe later. Okay. Like for example, if we take the integral of like x e negative x squared dx. We can use Actually, later we are going to have another method using the integration by part. But for now, by guessing, we can try and guess. We can try guessing from the e itself. Like if we take e, if we take the derivative of this, we are going to have e, right? And then the chain rule will be negative 2x. So it's getting there, right? It's getting there. We need to divide by negative 2, right? So then, since this, then the integration of x e negative x squared will be negative 1 over 2 e negative x squared plus c. How I get the negative 1 over 2? This is from here. Okay. I want to have this. How to get this from here? We have to multiply with negative 1 over 2. So then we can. Sometimes it's useful. Sometimes it's useful. Especially for a repeated function that can be derived, and it's always like bringing that part all the time. It's quite useful. So if you want to like solving the my exam questions with this method, it's okay. I'm allowing that because I think maybe some professor doesn't allow that. I checked some tutorial. You can also check the MIT. I forgot who is the professor. MIT, they also teach this one. This method. I got it from there, from the tutorial. You can go to the MIT website and you can see the video, or I think in the YouTube they also have it. You can check MIT Calculus 1 or Calculus. Oh yeah, Calculus 1. They'll have some tutorials because they have like several professors. I forgot which one, but I remember I watched it and then I know, oh, we can use this. Okay, I think I will just end up until here. Okay. So Thursday we are going to have some other exercise and then maybe some other method to solve the integral. Regardless, the techniques basically only have two main techniques: the substitution and integration by parts. The other techniques, they are supplementary, like using trigonometric identity and then using some partial fractions. But the main idea is on the substitution and integration by parts. Okay. Is there any question?